Welcome to this session of Zero Build Forum, which is organized first time in Turkey. I'm Professor Sermin Onaygil. My undergraduate education is electrical engineering. For more than 15 years, I have been working as the head of the Department of Energy Planning and Management at Istanbul Technical University Energy Institute. Because of this position, I had the opportunity to look at energy, especially energy efficiency, from a wide spectrum with a combination of different areas of expertise. The topics of the forum we are currently holding provide us good insights from the perspective of new technologies, renewable energy efficiency, of course, reduction of carbon dioxide. I am particularly pleased to be invited to this session as a moderator, and I would like to thank the organizing committee. With this forum held on online platforms, as you know, which I see as an opportunity. By the different pandemic period, we have the opportunity to meet many distinguished experts, practitioners, and decision makers, and to benefit from the valuable information. Therefore, once again, to the forum organizing committee, the technical team for their intensive efforts I have known. I would like to thank our speakers for their participation and information sharing. Without the audience, these initiatives will never achieve their aims. For this reason, we thank you very much for taking your time and listening this session. Before I give the microphone to our speaker, I would like to share some information regarding the functioning of the session. Our total session duration is 90 minutes. We have only one speaker for this session. We will give him 60 minutes of his presentation. 70 minutes will have been spent with the first introduction. We will consider the remaining 20 minutes as answering your questions. You can send your questions during the presentation. If that cannot be answered due to time constraints in the session, you can use our speaker via the LinkedIn link on the forum webpage. Biographies of all speakers and LinkedIn information are available on the forum website. I would like to say you can watch the Turkish translation of our English session on stream 2. Now it's time for the short introduction and presentation of our dear speaker. Today we will have a chance to listen to a very distinguished expert speaker, John Palmer. He is Research and Policy Director at the Passivhaus Trust. He authored Passivhaus, The Route to Zero Carbon, exploring how to ensure zero carbon targets result in zero emission buildings. John is a certified Passivhaus consultant, SAP assessor, system engineer, and experienced project manager. In practice, he has used fabric first principles to design and build living spaces that are comfortable, healthy, energy efficient, and easy to maintain. Prior to entering the construction sector, John spent 16 years as an engineering officer in the Royal Navy. John has determined the title of his presentation for today as Passivhaus, a route to net zero, in a way to reveal all of his experience. On behalf of all of us, I thank John for agreeing to be with us, to share his experiences and invaluable knowledge. I leave the screen to him to make his presentation. Okay, John, screen and microphone is yours. Please share the screen.
Simon, thank you very much. I'll just share my screen now. There we go. So hopefully you can see that.
Not yet.
Is that coming? Oh, hang on.
Okay.
How's that?
It's okay, John. You can start.
Great. Thank you very much. So, Simon, thank you very much for that very kind introduction, and thank you for the invitation to speak today. I'm really delighted to be able to present to you and all the people that are online. And as you say, this the ability to have an online forum really opens up our ability to communicate. So the title of my presentation is A Route to Net Zero, but there is a question mark at the end, and I really want to see if the audience thinks that Passivhaus also might be a route to net zero, and so that's what I'm going to go through today. I've got a number of sections to talk about. The first really is the big picture and where buildings fit into the overall climate emergency and net zero. Next, I'm going to spend just a few minutes talking about what Passivhaus is and what it achieves. Then I'm going to talk about where we are now in terms of how our buildings perform, because if you want to get to zero, it's always helpful to know where you're starting from, and then what we need to do to get to net zero and what net zero actually means when it comes to buildings. Then how we could get there, the options for getting there, and finally what we should be doing, some suggestions and some ideas. So let's get started with buildings and the climate emergency. So I think most people watching will be familiar with this graph that I've taken from the IPCC 2018 special report, which effectively said that we need to do that from 2018 onwards in order to avoid a warming below 1.5 degrees. And the key thing of this graph, about this graph for me, is that at that point in 2018, the graph doesn't carry on a little bit and then go down. It goes down straight away. So we need to be taking action right now to reduce emissions, rather than planning for things that might happen in 5 or 10 years' time and might help us reduce. We need to be reducing now, and we need to do what we know now is going to work. So that's my key takeaway from that that graph. I also wanted to point out that emissions from buildings generally fall into 2 broad categories. Either operational emissions or embodied emissions. Just, I'm sure most people are familiar with this, but just to clarify, the embodied emissions happen at the construction stage of the building, and also at certain points with maintenance and repair cycles during the lifetime of the building, and at the end. So on this chart there, the blue areas. Whereas the operational emissions occur during the lifetime of the building, and they're the emissions associated with heating, hot water, electricity use, etc. Today I'm going to be talking predominantly about operational emissions, because that's what Passivhaus focuses on, and that's also traditionally been the largest part of our emissions from buildings. But that's not to say that embodied emissions aren't also extremely important, because we need to get both down to zero if we're going to get to net zero. And as we reduce our operational emissions, embodied becomes more important. But they are complementary. You can do them both. One doesn't necessarily impact the other, and they need different types of consideration. So today I'll be talking about operational emissions. So how do buildings fit into the overall picture? Buildings account for nearly 40% of the world's emissions. And then you can see there that worldwide, the biggest chunk of that is in operational energy or operational emissions. So if we can deal with that, then we have gone, we've done our bit to get to net zero, if we can deal with part of that. And I just wanted to sort of put this up. You probably won't be able to read the detail, but it's just, this is very similar to the UK's pattern, but it's just to emphasize that there are mostly fossil fuel sources used in Turkey. And then if you trace those through, you can see the oil products, the gas and the electricity products. If you trace them through to the sort of residential section down here, you can see that the majority of the energy used in Turkish residential buildings use gas, oil and electricity as the energy sources. And similar to the UK, gas and oil are used for heating and hot water due to the fact that they're very efficient for doing that. But that's the challenge we've got to start with. The mix of energy that we've got right now, both in the UK and in Turkey, it is sourced from a lot of fossil fuels. So that is the big picture. Now I'd like to spend just a few minutes talking about Passivhaus itself. Some of you may have heard of it, some not. And there are also maybe some misconceptions because people think that Passivhaus is something that perhaps it's not. So what is Passivhaus? Well, I'm going to talk about all these different sections, the energy balance in a building, the criteria that are associated with Passivhaus, what Passivhaus does for health and comfort, quality assurance, and how much it costs. So let's start with energy balance. And this is a very simple but very powerful analogy. So if you have got a traditional coffee pot, which sits on a hot plate, then that will keep your coffee at the right temperature. But it is constantly pumping energy through that coffee pot to do that. So it's using a lot of energy. If you've got a very well insulated flask, that will also keep your coffee at the right temperature, but it's using no energy at all, or very little energy in some cases. So that is basically the principle of a Passivhaus. You put the energy in, keep the energy in rather than let the energy leak out. And of course, that is done in the main by improving the fabric, improving the bits of your building that are in contact with the outside world. In a typical UK home, and I couldn't find directly equivalent data for Turkey, but I think it's probably quite similar. You can see that we've got on the left-hand side of the screen here, you've got the ways that we can lose energy through a building. So through the roof, through ventilation, through windows and doors, through walls. So that's the way we can lose energy. On the other side, we've got ways we can gain energy. So we can gain energy through windows, through the solar gain, and internal gains. And those are what we do by living in the house, cooking, washing, and just our metabolic rates within the building. And then you can see that this large pinkish bit here is the gap, effectively. These two columns have to balance. And if they don't balance, if this one, the gains, is smaller than the losses, then your building will start to cool down. It will start to get cold. So the pink area is how much we need our heating system to deliver. And you can see here that for the UK, that gap for a new build home is around about 85 kilowatt hours per meter squared per year. It's probably worth me just explaining. I'm sure most of you will be very familiar with kilowatts and kilowatt hours, but there might be some who aren't, and I'm going to use them these phrases a lot during the presentation. So it's all about energy and power. So if we start off with power is measured in watts or kilowatts or terawatts. And it's an instantaneous measurement. So if you think of it like water, it's the rate at which water is flowing through a tap or a hose pipe or something. So that's power, and you measure it, and then the next second it might change, and it might change again. So I might have a light bulb, which is 100 watts. And so that means instantaneously it's putting out 100 watts of energy in the form of light and heat. Watt hours or kilowatt hours or terawatt hours is energy. And what that is power, but with a time function, which means if I left my 100-watt light bulb on for 1 hour, that would be 100 watt hours. If I had a 1 kilowatt kettle and I left it on for an hour, it's 1 kilowatt hour. So it's an area of it's a measure of amount of energy. So if I go back to water, power is the rate of flow of water. Energy is how much water you might have in a bucket or a glass. So kilowatt hours and kilowatts are power and energy. So what we've measured here is the amount of energy over the course of a year, and we also tend to measure it per meter squared of a building. And what that means is we can compare different sizes of buildings. So a small building and a large building, very difficult to compare the amount of energy they use overall, because the bigger one obviously will use more. But if we reduce it to per meter squared of the building, then we can compare all different types of buildings and different sizes of buildings. So in the UK, it's around 85 is what our new build systems have to deliver. Existing buildings, the buildings that are already built, it'll be a lot more. So what does Passivhaus do? Well, Passivhaus comes along and really focuses on that left-hand side of the chart, on all our losses. What it does is it squashes those down. So more insulation, better ventilation, better windows, no thermal bridges. I'll explain those in a moment. So that really gets squashed down. And on the other side, what happens is the solar gains and the internal gains stay are roughly the same, which means that this small bit now is all the heating system has to do. And that comes down to 15. And that 15 number is the specific Passivhaus criteria that has to be met for that building to be known or certified as a Passivhaus. So that's really in a nutshell, that's what Passivhaus does. It makes the fabric better to reduce your heating demand. But it does some other things as well. And I wanted to put this slide up just to show the fact that Passivhaus is not just about energy. So we spoke to just now, I mentioned the magic number of 15, and you can see that is indeed related to energy, but it's also related to comfort, because it's very nice to have a warm, comfortable home without lots of drafts and variations in temperature. And you can see there are other criteria there, which are, again, not just energy related, but focused on comfort. And this is one of the big misconceptions of Passivhaus, is that it's just about energy. Actually, it really focuses on comfort as well. So air tightness helps with energy, but it also means there are no cold drafts. Our surface temperatures above 17, which means we don't get condensation and mold in our house, so it improves the air quality. Summer overheating, less than 10%, which means that we've got nice temperate buildings all the year round, etc., etc. So you can see that it's not just about energy. And if we translate that into what it's like to live in this kind of building, you can see that on the left-hand side, we've got those kind of Passivhaus criteria, what we're specifying right at the beginning. That leads to these effects. I already mentioned the condensation and mold. The air quality is very good because all the air is filtered and coming into the building and controlled. And the result is warm, comfortable buildings with healthy indoor air quality, which are comfortable in the summer. And that might sound great, and we might think that we are already building buildings like that. But actually, the alternatives, which are cold homes and homes that overheat and homes with poor air quality, already exist. And actually, certainly in the UK, some of the homes that are being built as new homes still suffer from these problems, particularly overheating. So this isn't something that we've already solved. Passivhaus comes along and will guarantee this. And talking of guarantees, I just wanted to talk a little bit about the performance gap. Again, I'm sure many of you will be familiar with this, but the performance gap is the difference between what we design and what we model at design stage and what actually happens when we get the building built. And this little chart comes from quite an interesting study which looked at where the performance gap occurs. And many people think that the performance gap always occurs on the building site, that when you entrust the design to your builder, they get it wrong, and that's why buildings don't perform. But actually what this shows is that the gap starts to happen in design stage, And what this graph is showing is that the y-axis, the 0 axis here, is where we hit the regulatory limit. So that's what we have to be above. We start off well above it, but when we start to get into sort of stage 3 and 4 of the design of the construction process, where we're doing develop design, technical design, things tend to get quite difficult, and we're making trade-offs, and we're making compromises, and at that point people aren't necessarily looking at energy. They're often looking at cost or other elements, and what that means is that almost inadvertently the performance of the building starts to dip, and by the time we actually get to site we're already below the line, we then get on site, and then things do happen. Things perhaps aren't built correctly to the specification, different materials are substituted, and we carry on dipping in performance until by the time the building is occupied, it's well below what we expected it to be, and that is the performance gap. So I found that quite interesting, and it's interesting then to map that against what Passivhaus does. So Passivhaus has these criteria, which I've spoken about, but it also has a built-in quality assurance process. And what that means is that correctly qualified people, designers and certifiers and tradespeople, are involved in the process step by step. And up at the beginning here, where you've got a stage 1 and 2, you've got a Passivhaus designer on board. They may well be your best friend as the design team, because they're telling you that, yes, you've met the criteria and your building is going to be a Passivhaus building. Down here in sort of technical design, they're your worst nightmare, because in that case they're saying, no, you can't do that, or it won't be a Passivhaus. And that's what stops the performance gap. It stops people inadvertently changing things which compromise the energy performance. And the net result of that quality assurance process throughout the Passivhaus project means that we don't have a performance gap on average in Passivhaus buildings. And this is a very famous chart in the Passivhaus community. And it shows 3 here on the right-hand side, 3 Passivhaus developments. And you can see in each one, the red line and the black line, one is the calculated space heating demand, and the red is the average of the actual measured space heating demand. And you can see that they're right on top of each other. So some buildings are more than others, so there is a distribution, but on average, the space heating demand in a population of Passivhaus buildings is exactly as the design says it would be on 15. So there is no performance gap, and that's really important. In the UK, it's a great problem for us, and the performance gap, and you can set as many standards as you want, but if you don't fix the performance gap as well, then what you're building will still use more energy and you won't get to net zero. Does it cost more? Well, it can do, I guess, is the answer. So this is just a chart showing the extra over and under costs of various elements of a Passivhaus project. And you can see that there's a little bit more generally in insulation. There's a chunk in the MVHR, which is the mechanical ventilation heat recovery. And there's normally a saving in heating hot water because there's less of that in the building. I would argue a little bit with MVHR being an extra Passivhaus cost. Because what MVHR is delivering is your ventilation, fresh air quality. Is that something that you would expect not to pay for, because you don't really get that in a normal building? So overall, fairly containable costs. If we look at where we've come from in the UK, our pioneer projects were quite expensive. We didn't really know what this needed, what this required. But by 2018, we were down to 8%, and projection is down to 4%. And there was a report that came out last week, which put current costs at around 5.3% of this kind of building. But actually, I would also say that there are some people who have built to less than that, or to cost neutral. And what they say is that actually what Passivhaus does is it forces you to build simply, it forces you to build robustly. And what that does is that saves you money on what you would have built otherwise, which means that you can actually get it to be a cost neutral exercise. And of course, that's just build costs. If you take into account the lifetime costs, then you will always generate a positive result. So here we're showing where you start with different kinds of passive house with different heat sources. So a gas boiler, an air source heat pump for electricity, a Passive House Plus or Premium building, which is two different elements in the Passive House standard. And you can see that there's an extra cost to start with, so you're below what you would have otherwise paid in the negative. But as you use the building, your savings on energy and also, in fact, maintenance will result in the comparison coming back up. So within about sort of 11 years in those two cases, 16 in the other case, you will be above the line, and then you'll be in a better financial situation after that over the lifetime of the building. So those are some of the defining principles of a passive house. I now wanted to look at what it takes to build a passive house. So we'll talk about orientation, we'll talk about form factor, orientation, insulation, air tightness, thermal bridging, and ventilation. So form factor. Form factor is actually nothing to do with passive house in a way, but it makes passive house much easier. And what form factor is it's a single number, and it's a ratio of the external heat loss area to your internal livable area. So livable floor area and external heat loss area, one divided by the other. So for this building that I'm showing now, you can see that the floor area is 93 meters squared and the heat loss area is 279, 280 meters squared. So that's heat loss area is all the parts of the building that are in contact with the outside world, through which in the winter season we're losing heat. This building has exactly the same floor area, 93 meters squared, but it has only 74 meters squared of heat loss area, so it's 4 times less. Now, yes, the top flat will have a roof area, the bottom flat will have a floor area, but overall, every unit in that building will have a lower heat loss area than if it was built equivalently as a standalone building. And what that means is before you even start thinking about insulation and energy performance, your job is 4 times easier. 4 times thinner insulation to get the same amount of heat loss because you've got 4 times less heat loss area. So that's just purely efficiency of shape. So if your form factor is good, and in the UK, generally we can get anything sort of 2.5, the number 2.5 form factor and below is relatively straightforward to achieve passive house. If we get above that, it starts to get more difficult, more costly, and that's not where we want to go. We want to start with an efficient building. Next, orientation. This isn't just orientation of the building. In fact, the building itself can point any way you want. It's more the glazing. It's more where your windows are pointing. So what you can see here is we've got an apartment with its glazing starting off on the southerly elevation, and the blue shading in the background shows the heat demand for that building. And you can see it's just below our number of 15 here. All we then do is rotate that building through the compass until it's now pointing north. And you can see that the heat demand goes up correspondingly. So we haven't changed the level of insulation, we haven't changed the heating system, we haven't changed anything else in that building. All we've done is rotate it round, and you can see the heat loss has almost doubled because we've now got too much glazing on the north side and too little glazing on the south side. So again, that's not really anything to do with passive house, but if you get that right to start with, the optimum amount of glazing in the right orientation, then it makes everything else easier later on. And the other thing about orientation is it also helps us deal with summer overheating, which in a changing climate is an increasing issue for us all to consider. And what you can see here is this is the amount of solar energy that's getting through onto the surface of this window. And you can see that for the south, when this window and the overhang is facing south, in the summer case, only 20% of the energy of the sun is getting through to that window, whereas in the winter case, over 60% is getting through. So that's exactly what we want. We want in the cooler times of parts of the year, we want assistance from the sun to keep our buildings warm, and in the summer when it's too much energy, we want to keep that out. So you can see that when it's facing south, this shading works very well. When we move to east or west, then you can see that it's almost the same. And that means that the shading is not working as effectively because the sun comes around and it's low. So that gives us a problem. So again, orientation is really important, and it's good to get your glazing and your shading in the right place, which again makes our job easier. So now I want to talk about the principles of Passivhaus itself. The first one might sound obvious, but it's continuous insulation. So continuous insulation all around the building, all those elements that are in contact with the outside air or the outside ground. And in the UK climate, that's typically around 500 millimeters for the whole structure of the wall, including the insulation. But you can see there are some small gaps there, and those are thermal bridges. Those occur typically where the structure passes through the insulation layer, and in a normal house, it doesn't give us much of an issue. In a Passivhaus, it can add up and have a major effect. So we need to get rid of those, and the way we tend to get rid of those is designing them out. Clever design, intelligent design, in some cases specialist materials, but they can be done very inexpensively. They can be designed out. Next, glazing. We have a couple of reasons why we use triple glazing in Passivhouses in the UK. The first is to keep as much as possible of the heat in, so they're much better than double glazing or single glazing for keeping heat in the building. And it also means that the surface temperature of that glass is 17 degrees or more all year round. And what that means is that we don't feel cold when we're sitting next to a window. So if we were sitting next to a double glazed window in winter, which might be 12 degrees, we'd feel cold, even though the temperature in the room may be fine, because we're feeling that surface temperature from the window. So triple glazing addresses that, and also the shading. Next, air tightness. I mentioned earlier on that Passivhaus buildings are airtight as one of the criteria. They are very airtight, about 10 times more than a typical building. And what that does is it keeps all our warm air in, which is great from an energy point of view, but it also prevents any cold drafts coming in and making us feel uncomfortable. And then finally, we've just made our building very, very airtight, which means that that needs to then be sorted out in terms of our ventilation. So we put in a mechanical ventilation and heat recovery system, which is constantly extracting our warm but perhaps stale or humid or smelly air out of the building, passing it over a heat exchanger with cool air coming from outside and using that air to heat the building. In summer, it reverses. You've got warmer air outside and cooler air inside. It works in the same way. The heat exchanger just does the same job. And what this means is that without losing energy, either cool air or warm air, we are maintaining a constant flow of fresh, clean, filtered air into our building. And this is one of the significant points which is improving people's health and comfort in buildings. And I was listening just yesterday, about people saying that their children who have asthma move to a Passivhaus, and their asthma sort of clears up, disappears. So that's a little bit about Passivhaus. What I'm now going to do is talk more about the kind of bigger picture and what it might take us to get to net zero. So as I said earlier, if we are trying to get to net zero, then it makes sense to understand where we are right now. So this is a little just waterfall diagram which explains the various ways in which we use energy in a residential domestic building. We start off with our heating, usually the biggest chunk, and I mentioned it earlier, the performance gap. We can't ignore it, and it in the UK we think it's about 60% of our heating demand. So we model at 54 kilowatt hours per meter squared per year. So that's a typical average building when it comes out of design. When it's in use and you measure it, it turns out it's 60% more energy use. So that takes us up to 86. Next is hot water, then lighting and pumps and fans and some minor things. And then finally, appliances. So anything that we plug in, washing machines, fridges, that kind of thing. So that's really how we can break down, and that's the proportion that we seem to be at the moment. So I'd now like to sort of pose you a question, really, which is if we are thinking about how we set our targets for the future for buildings, should we be talking about carbon, setting targets in terms of carbon, or should we be talking about energy? And I wonder what what your personal thoughts are on that, because most people will instinctively say carbon because that's what we need to try and reduce and get to zero. But actually, I would suggest that the answer should be energy. And the reason for that is that energy is a much more reliable indicator. So let me explain. So if this was a 1 kilowatt light bulb, then if we left this on for 1 hour, how much carbon would it release? Well, we know at the moment, because we can monitor our electricity grids, and this is the UK's grid, a snapshot from a few months ago, and you can see that most of our energy at this point was coming from gas, then solar, nuclear, etc. And the figure there was 211. So 211 grams of CO2 gets released for every kilowatt hour. So if I left that light bulb, 1 kilowatt light bulb on for 1 hour, 200 grams of CO2. So, that would seem pretty straightforward, pretty simple. Why not set targets in terms of carbon? Well, the problem is that later on that day, the number was different. The number changes minute to minute, and it changes because we've got different amount of mix going in, and particularly our renewable sources. So wind and solar is not very reliable in that we can't predict it from week to week. So at this point, the sun had gone down, no solar, so my number had gone up. And what about next week or next year? Do we know what's going to happen in terms of national policy? Is the government going to introduce lots and lots and lots more renewable energy, or perhaps we'll have a new government next year and they won't? So predicting forward to 2050, both sort of on a short term and long term for carbon is quite difficult. In contrast, if we look at, if we compare that with energy, right now, we know with carbon, those figures I put up somewhere between 150 and 298 on that particular day. Energy, it's a 1 kilowatt hour. And in 2050, we don't know for carbon, but we do know that it will still be 1 kilowatt hour for a light bulb. And what that means is that if we set targets in terms of kilowatt hours for energy efficiency, if we build an energy efficient building now, it will be an energy efficient building in 2050. And there was a great example from Vancouver, where a building which was cited as an exemplar low energy building passed their code with flying colors. A few years later, when their grid had decarbonized, it turned out that this building wouldn't have passed building regs because it was using too much fossil fuel, regardless of the actual, and it wasn't very efficient. So picking your targets in terms of carbon has got a number of issues. Not to say we don't monitor carbon and we keep an eye on it, because that is the end goal, but setting targets, I think, should be in energy. So let's now go back to our talking about net zero. So I explained earlier about the way we use energy in buildings. So if you want to be net zero, then we need to offset one with the other. Offset generation. So if we've got renewable generation from whatever source, that needs to match how much energy we use in the building. But you may notice that there's one bit sort of missing here that I talked about earlier, which is those appliance loads. And traditionally, they have been ignored because actually they are quite difficult to predict. We can model heat use. We kind of know how people like to heat and cool their homes. We can do the same with hot water and lighting, but appliances is more difficult. So it's tended to be ignored because it's so dependent on how people use their buildings. But I would argue that now we're in a net zero world, we can't ignore that. So we need to bring that into play as well. So that means that all those elements, heating, hot water, lighting, and appliances, all need to be considered when we work out how much renewable energy we are going to need in the future. So is that it? Is that what I'm showing on the screen now for that typical home? If we generated 132 kilowatt hours per meter squared per year, would that be net zero? Well, the problem is that we need to consider something else. And the thing we need to consider is what our energy systems might look like in the future. And they might look something like this. And you can see this is a little bit similar to the diagram I put up at the beginning, with sources of energy on the left-hand side and where they go on the right-hand side. And you can see that in the future, when we are in a net zero world, we are not burning things. We are not burning fossil fuels. We're not burning things that come out of the ground, because we can't really do that and still be net zero. So what we are doing is we're generating a lot of renewable energy from a variety of sources. It might be solar, it might be wind, it might be tidal. And then, but the problem with that is that they are not predictable and reliable, as I've mentioned. So when there is a national holiday or a great sporting event or something like that, we can't guarantee that at a particular moment when everybody wants to come and make some tea or whatever it might be, we have got that extra energy available from the wind or the sun. So what that means is we have to store our renewable energy. Some of it we will have to store on a daily cycle, so we'll generate during the day and we'll use it in the evening or overnight. Some we might store interseasonally, so we might generate in the summer and use it in the winter. And that presents a problem, because if we store energy, generally we lose energy. We'll lose it in the transmission into storage, we'll lose it during storage, and then getting out again. And at the moment, we don't quite know how much that's going to be, because we don't know what national grid scale storage technologies are coming along. And we also don't know the characteristics of our future buildings. So how long do we need to store energy for? Have we got very efficient buildings which don't need to store energy for very long, or not? So that makes it quite difficult to predict, but nevertheless, we need to bear it in mind. So actually, when we're thinking about net zero, we need to consider not only the energy use in the building, but the storage losses associated with that. And what I mean is, if we need 100 kilowatt hours to run a building over the course of a year, then actually we might need to generate 120 kilowatt hours or 130 kilowatt hours in order to take care of those storage losses that are associated with it. So this is a bit of a developing area, but it's definitely part of the net zero discussion. So you can see here that my actual net zero definition has become not only what we use in the building, but the storage losses. And if we now generate that total number, 184 kilowatt hours per meter squared per year, then we can consider this building to be net zero. So we have talked about where we are now and what net zero is, my definition of net zero. You may or may not agree with me. We'll perhaps see at the end. So now let's talk a little bit about how we could get there. And it's actually quite difficult. I'd like to sort of talk about this section in two different ways. The first challenge we've got is our new build homes, so new housing stock, and the other is our existing homes. Some of them old and run down like this, but others may be fairly modern, but they probably are still using too much energy. And we need to talk about them in a couple of different ways. So let's think about how we could solve this problem of net zero. Well, the first way we could do this is we could just wait for our electricity grids to decarbonize. So I showed you the energy flows at the beginning, and what we know is that all countries are looking to introduce more and more renewable energy sources into the national grid, their electricity grid, and what that means. This is the projection for the UK. We may or may not follow this. We may or may not get there. We need to, but this is the projection, and this shows us that the grid content, the amount of carbon that's associated with electricity, is decreasing fairly rapidly all the way to 2050. So what we could do is we could just wait for this to happen and have it solved at a national level, which means we don't need to do anything difficult or different with our buildings. Wouldn't that be great? Well, the problem is that it's not quite that simple. This is the equivalent energy flow diagram for the UK. I just want to pick up again on this domestic, the residential domestic bit there. And you can see that a large chunk of that is coming through from natural gas in the purple at the top. And then a much smaller element of it is electrical in the pink. So if we, so in the pink. And what that means is that there is a huge chunk, and it's 84% of UK homes. And it was, I think it was fairly similar, but not just gas, but oil as well for Turkey, are heated and have hot water provided by natural gas. And the problem is we can wait for as long as we want for the electricity grid to decarbonize, but that's not going to affect gas. And gas will still be pumping out lots of fossil fuel emissions. So that means that we need to move from things like this, gas or oil boilers, fossil fuel sources, to something like this, which is an air source heat pump, which uses electricity. So that's going to solve the problem, isn't it? So this is it's going to be a lot of air source heat pumps, take out a lot of boilers, but that's perhaps the way to do it. And again, we don't need to do anything else with the buildings. Well, there are a few problems with this, and the first one concerns peak load. So we're back into talking about power, instantaneous power in watts or gigawatts in this case. So, and this is a UK example, but it illustrates it very well. If we added 15 kilowatts of extra electricity load for every house in the UK, so we're now saying that we've taken out our gas boiler, so we need to provide our heating and hot water by an electrical system. And we're going to say that's going to use 15 kilowatts of energy. If we did that in every house in the UK, and if they all came on at roughly the same time in the morning on a cold winter's day, that would add 125 gigawatts to the load of the national grid at that point in time. Right now, in 2050, the entire capacity of the national grid is only 100 gigawatts. So that shows you that just switching all our domestic heating over to electrical in one swoop just isn't possible with the current capacity of the grid. And even in 2050, where our grid is scoped to increase quite significantly, it's still too big a chunk, because that 2050 figure is where everybody, all the other sectors, are also needing to draw on this clean energy from our national grid, from our electricity grid. So transportation, aviation, all our industry, commerce, that will be needing to draw its energy from there as well. So it's just not feasible to switch everything from fossil fuel to electricity without some other changes. So the other thing we could do is we could just throw more renewables at the problem. Just say, right, okay, that's fine. We're going to build more and more wind turbines. We're going to put more and more solar out there. And perhaps we can try some tidal, whatever it might be. Well, is that the right answer? So if you're trying to get to zero, you have a couple of options. You can carry on using a large amount of energy, which is, to be honest, what we all do at the moment. Or you can invest in your energy efficiency and use far less energy. But you have invested quite a lot in order to make that building energy efficient in the first place. So for those two options, when you come to trying to make those two buildings net zero, for the first option, you have to generate a lot of renewable energy. For the second, you only have to generate a small amount. So both those options are viable. They will both work. But how does that look from a financial point of view? Well, the thing about energy efficiency is that when you invest in that, you're investing in the fabric of the building right at the start of the building's lifetime. So if you're putting more insulation and better quality fabric in right at the start, that's going to be there for the next 40, 50, 60, 80 years, perhaps, the lifetime of that building. And it's going to be working for you the whole time. And you've paid for that once. However, if you have to generate the same amount of energy, then that will come from offshore wind, air source heat pumps, photovoltaic, ground source heat pumps. They all have a lifetime of around 20 years. And what that means is you have to replace them 2, 3, 4 times perhaps during the lifetime of the building. And that will generate additional costs. So what this chart is showing is that it actually costs less to save energy at the start than generate it all the way through the lifetime of the building. And that's not the whole story. Oops. That's not the whole story. Actually, there's something else we need to take into account. If we look ahead at what the UK's forecast is, what I've done here is this is the amount of energy we would need if every home in the UK was Passivhaus. We're sitting at around 45 kilowatt hours per meter squared per year. In 2030, we think we're going to have just over 40 kilowatt hours per meter squared per year. And in 2050, it's going to be a little bit higher than that. So this is really quite interesting, because what this is saying is that even if every home in the UK was Passivhaus, on current projections, we wouldn't quite have enough renewable energy to make the overall equation, or the overall sum, zero energy in either 2030 or 2050. And of course, that's every home. That's not just the new homes we're building, that's the existing homes as well. And, you know, enthusiastic as I am about Passivhaus, the chances of us being able to get every existing home to Passivhaus levels is pretty slim. So what this tells us is that it's difficult. And at the moment, our projections are showing that we don't have enough renewable energy in the future, not even close to get our buildings down to net zero. So we've had a couple of options. Throw renewables at the problem. We can wait for the grid to decarbonize. The other option perhaps is we could just introduce legislation. We could just say that we would like to mandate every building to be net zero, force people to build net zero buildings. Now that would seem like a really good idea, wouldn't it? Because that takes the problem down to the design and the builder level, and that pushes it down to make everyone behave well. Well, I would suggest that the answer there is that's not right. And this is why. So what I've done on this chart is I've taken what we were dealing with before, which was kilowatt hours per meter squared per year, and I've multiplied it by the actual area of a building, 68 meter squared building. So this is now actual energy, kilowatt hours per year. And you can see that for our Passivhaus, and these are everything I've been talking about so far, heating, hot water, lighting, and unregulated energy and storage losses, that adds up to just under 4,000 kilowatt hours in a year. So going back to our definition of net zero, that means quite simply that we need to generate that amount of energy in order to get to net zero. So that's simple. But the problem is that to generate that, we need around 14 solar panels. And solar panels take up space. So if we look at how that actually stacks up, you can see that here are, the top left are our 14 solar panels. If we put them on a single story, 68 meter square building, everything works fine. If we make that 2 stories, then it doesn't actually fit. If we make it 3 stories, which is for this size of building apartment, more logical. In fact, it might be 8, 10, 12. You know, the 68 meters squared is just a sort of a 2-bedroom apartment. If we put it on there, then you can see that it doesn't fit at all. So we've got a problem there, haven't we? So what are we trying to do? So if you remember back to my discussion of form factor, you will recall that this type of building, single story, is really inefficient. Before we even start, it's inefficient. It takes more insulation, more cost to get it to be a highly performing building. Whereas this form factor is much more efficient. So if we force people to build what's actually a net zero building, we actually force them to build inefficiently. If we let people build efficiently, what we need to consider is that, yes, we still need that amount of generation of renewable energy, but perhaps it doesn't necessarily need to go on the building. Perhaps it can be elsewhere. And this is all about the system boundary. Do you consider the system boundary around your building? Do you consider it around your development, your site? Do you consider it around your region or country or world, whatever. But the point is that if we try and make every single building net zero, then we force people to build inefficient buildings. Actually, we need to look at the big picture and see if we've got enough renewable energy across our whole scope, and see if that net zero equation works. So I mentioned about new build and retrofit, and retrofit is the next thing I'd like to touch on. You can see that it's a different challenge, and actually it is the bigger challenge, and this is the reason why. This is the England housing stock from 1990 to 2050, and 1990 is where the Kyoto Treaty is based upon, and that's why we have percentage reductions from that era. It's also when the UK sort of energy regulations really started to come into building regs in significantly. But actually, even the buildings we are building now are not, as you've just seen, not energy efficient enough for what we need to do to get to net zero. And what that means is every building we are building right now will need to be retrofitted before 2050. And if you see where we are in 2020, we're about here. So the new buildings that we're going to add between now and 2050 are just the sort of orangey, red and dark blue ones right at the tops. And that's a really small number compared to all the other buildings we've got. So dealing with our existing buildings is the biggest challenge, because it is far more difficult to get them up to a higher energy standard, and there are far more of them to deal with as well. And the challenge is just huge. So this is the UK's challenge. Obviously, it will be different for Turkey, but this gives you an idea of the scale. So if we started on the 1st of January 2020, and we retrofitted one of our domestic buildings every 35 seconds, we would just have finished by the time we get to the 31st of December 2050. But that's a bit of a silly metric because we don't retrofit one after the other. We do them in parallel. So let's say each retrofit took 6 months. If that's the case, then we would need to have 500,000 retrofits running at the same time, simultaneously, between now and 2050. And if each one of those retrofits took 6 months and took 4 people to do it, then we'd need 2 million people working in the retrofit industry. And currently in the UK, we have around 135,000. So you can see that the challenge of retrofit is huge, and it's completely different from the challenge of new build in terms of how we have to approach it. So I guess I've painted up to this point a little bit of a somber picture, a difficult picture. And I guess if Greta was watching, she wouldn't be too happy with what we've achieved and where we are. So let's finish off with what we should be doing, and perhaps look at some of the ways in which we could actually achieve this moving forward. So once again, an energy flow diagram, and this is from a recent publication from the UK's National Energy Grid, where they model a number of future scenarios and see how many of those might get us to net zero. And it's in the same format as we've seen so far, which is energy sources on the left-hand side and where they go on the right-hand side. And this is one of the scenarios which meets net zero, so it gets us there. There are a couple of others that don't, but this one that does. And you can see that it's pretty similar to what I was hinting at earlier, which is that we've got a series of renewable sources here. We've also got a little bit of nuclear and a small amount of gas, and that flows through. And certainly in our residential sector, we've got mostly electricity, a little bit of biomass and a little bit of hydrogen. But the key point to note is that, and you probably can't remember the figures from earlier, but this number here is significantly smaller than it is now in terms of the overall energy use. So that just goes back to my point of, points of peak load. We can't just electrify everything, and also points of how much have we got? How much renewable energy will there be in the future? So in order to make this work and to fit our houses alongside all our industry, commerce, our transport requirements, we need to reduce. And there is a great quote from this particular report, which says that energy efficiency is a no regrets measure for all scenarios. So what we're saying there is that it doesn't matter how you're going to get to net zero, because there are other options. There's hydrogen heavy, there's other ways of doing this. Any option, if you make your buildings energy efficient, it helps. It helps significantly. And in most options, you can't get there unless you make your buildings energy efficient, which I think is a great quote. So let's go back to our new build versus retrofit. So new build, to be honest, it's very straightforward for me. We know that we probably won't have enough renewable energy unless we get down to very, very efficient levels. So for a new build, we need to be building as efficiently as we possibly can. And anything less means we're going to have to retrofit that home again before we get to 2050. So as efficient as we can, and renewables should be encouraged, but not mandated, because we need to look at that bigger picture. So that's new build, relatively straightforward. Retrofit is much more complicated. So when do you intervene in retrofit? Because somebody will own the building and they have a vote. There are risks to retrofit. How much does retrofit cost? Who pays? Are people confident in the tradespeople that come and do it? So it starts to get very complicated. So perhaps we need to look at it in a more nuanced way. So this is some different types of housing we have in the UK. We'd like to know where we are now in terms of what energy our existing buildings use and how much we could save. So perhaps in some of our very old buildings, we can't do that well, but some of the later buildings, we can do a lot better. So that's perhaps where we should be putting our effort. It also could be that we look at it in the shape of buildings. So should we be looking at the detached buildings or whatever it might be? And should we be looking at shallow retrofits where we just do a little bit of insulation in the attic, in the loft, or should we be looking at a deep retrofit? We don't know. Because we need to get to some of this kind of figure where we're looking at how much it costs per building type to save a kilowatt hour. And what that will do is that will inform our big picture, which is how far can we reduce our energy demand in the built environment? And then that informs policy at a national scale, which is here's how much renewable energy we are going to need in the future if you do want to get to net zero. So I've spoken a couple of times about hydrogen. I mentioned. So are there technologies which are going to come along, which means we don't need to do this energy efficiency thing, because it is difficult. It's not easy. So are we going to get hydrogen boilers coming in and saving the day? Could we have more efficient heat pumps, high temperature heat pumps, things which means we don't have to do energy efficiency, or solar panels, which are 5,000% more efficient? Well, lots of these things have been worked on for many years, and the technology is relatively mature. We may see incremental improvements, but I'm not sure we're going to see something that's going to come along and just solve all the problems for us. In particular, I wanted to mention hydrogen. I know we've only got a few minutes left now, but what I wanted to show here is that there are various supposed forms of hydrogen, and the only true green or CO2 free hydrogen is green hydrogen, and that's hydrogen which is produced from electrolysis. So we use renewable electricity generated from renewable sources to produce hydrogen. Everything else results in CO2 emissions, which either go into the atmosphere or they have to be captured and stored, and we can't do that at scale yet. And the investment to be able to do that at scale is massive. If we just look on the right here, you can see that if we start off with our renewable energy, which we're generating, and the first option is we put it through a grid to people's homes, and we combine that with a heat pump, and that gives us a multiplier. And so if we start off with 100 kilowatt hours, we're going to end up with 270 kilowatt hours. So it's a 270% efficient process, depending obviously on your type of heat pump. Alternatively, we can take that same 100 kilowatt hours of electricity and we can convert it to AC to DC. We can then use some electrolysis to produce hydrogen. We then store, compress, and transport the hydrogen. And at each stage, there are losses. And by the time we put that through our hydrogen boiler in someone's home, we're down to 46 kilowatt hours meter squared. So what that means is, you remember that I spoke earlier about the fact that we probably haven't got enough renewable energy already, and that this is kind of based on the electricity, the heat pump scenario. This, if we use hydrogen, we need 5 to 6 times more renewable energy to start with, which is just not feasible. And that's why, if I just flick back a few slides, that's why this particular scenario shows a very small amount of hydrogen. That's for very hard to treat homes, homes which we can't get the energy demand out, homes which are off grid, very small amount of hydrogen. The vast majority are on electrical supplies. So hydrogen is really going to be needed, again, as this diagram shows, where we really need that high power to weight ratio in aviation, shipping and transport. And that's where hydrogen is going to come in. So it really brings me back to my initial diagram, is that we can't afford to wait. We need to start right now. We need to start moving this down. We can't wait for hydrogen to come along in 10 years time and then find out it's not going to work. Energy efficiency, as was said, is a no regrets measure, which means that we are able to do it now, and it will have a significantly positive impact in all possible scenarios. So thank you very much. That's my concludes my presentation, and I believe now we are opening up to see if anybody has any questions.
Okay, it's really nice. I would like to thank John for this truly informative. It's really, I'm very happy because it's with an engineering approach. It's good to give some information. What can we do and what is the reality? It's okay. Now it's the time is the question and answer, and you mentioned the end of the presentation. Now I'm looking to the screen, and because our station responsible people, Yasemin Somuncu, will give you some questions. Now we have one question. It's how much more would a net zero passive house cost of compared to the conventional building? As I remember that you have already presented a slide compare with the cost with the conventional or in a passive house,
so,
net zero house. 80% or
yeah, so at the moment it's somewhere between 8 and 4%. But it's interesting that the question quite clearly states to get to net zero, and that's a different answer because exactly. So if you build a passive house versus a conventional building, we think at the moment it's around 4% more to build to passive house. But then if you then want to move on and make that building net zero, it's a different question, because if you go back to my slides where I showed you a passive house compared to a typical building, the amount of energy from in the UK is for a typical building versus passive house is double. So in a typical building, you might recall I said, I gave you the example of that 68 meter square building, which was, if it was passive house, would need 14 solar panels. If that was a non-passive house, a typical building, conventional building, it would need 28 solar panels. So it would need double the amount of panels to get it to net zero. So first of all, you've got the additional cost of doubling your solar panels. Then you've got the fact that every 20 years, those solar panels need replacing. So if you add all that up, it's actually much more expensive to build to conventional and then try and get it to net zero than it is to build to passive house and get that to net zero, which is much cheaper throughout the lifetime of the building.
Yes, it's not easy to say this just the value of, yes, of course, I can understand. It depends on the type of the building and depends on the functional of the building. Everything is affected, of course. You have mentioned also your presentation about the orientation of the building and the size of the building. There are many parameters can affect to find the just good answer of this subject. Of course, maybe it's clear now. It depends on the project. Of course, we need some life cost and life cycle cost.
Yeah. So yeah, I was going to say, so as you mentioned, orientation of the building and the size of the building is really important. But obviously, people watching today, I guess, might be architects, designers, clients, construction people. You very rarely get to a project where it's easy to make everything work, easy to get the orientation right, easy to get the glazing right. So there are always compromises. But what we have found is that if you don't, if you at least explain to clients right at the beginning what a massive difference this makes, getting the orientation right, getting the amount of glazing right, what difference it makes, then very often they come round and they're happy to have the design optimized to be changed to match. But if people don't know to start with, then they're not going to make any kind of decision. They're just going to carry on doing what they're doing before. And one great example is in larger buildings.
What's the problem of the pole? I think we have some problem to connect the pole.
Have I come back? Sorry.
Okay. Welcome. Yes. Okay.
I was just saying that one of the sort of classic things you see in larger buildings is in larger cities is sort of floor to ceiling glazing windows, very large windows, because that's fashionable and that's a modern look. But actually, that's really bad from a energy point of view, because the glazing will lose you lots of energy when it's cold, and it will make it too hot in the summer. So what you will see is that reducing that amount of glazing is a win-win-win situation. So it's cost less because glass is very expensive. Walls are generally cheaper than windows. It means the energy bill of the building will go down, and it's often easier to build as well. So reducing that glazing helps everybody. And it was interesting that the mayor of New York about 6 months ago actually put in legislation that you couldn't put in floor to ceiling glazing in any new tower blocks because it's just too expensive.
Yes, of course. Yes, we have a question. I think it's the same subject. It is how soon should a passive house building pay for itself?
So there's a number of sort of variables which affect that. So the first variable is how much extra it costs to build. So I said average is about 4%, or coming down to 4%. But I also mentioned that there are some projects which have got it lower than that because they have optimized the design. So if you start off with a big inefficient shape and a complicated shape, that would have cost more to build than the simple shape. And that offsets the extra cost of triple glazing or ventilation. So in some cases it can be less. So how much extra you have paid to start with is a key factor. The next the other factor obviously is, what are you saving on your energy bill? So what would the energy use have been of your original building? And that very much depends on your building regulations, your building code, and how efficient the buildings that you are building right now. So we think that's about half for UK. It might be more in other parts. So those are the two factors. How much have you paid extra? how much are you going to save? There is another factor, which is maintenance. So what we find is that the whole quality assurance process that goes with Passivhaus means that the building that you get is a better quality building. And therefore you need to replace things less often, and you need to go back and repair things less often. So there's a great quote from Exeter Council, which is a region in the UK. They started building in 2010, 2011, and they say they haven't been back to replace anything in their buildings so far. They've lasted. So there's a maintenance saving, there's an energy saving. So if you just add up those two things, then we think it's somewhere between 10 and 15 years maximum for the payback. But it could be a lot less if you've paid less to begin with. But there is also one final bit which is really difficult to turn into money, and that's the health and well-being benefits of living in a better environment. So you're living in a building with fresh, clean air, filtered air. You haven't got any cold spots. It's much more comfortable. And I gave that example during the presentation of someone whose children's asthma had cleared up as soon as they moved into a Passivhaus. So that's very difficult to put a value on. But nevertheless, it's still very important, and it's something which is part of the benefits that you get from a Passivhaus.
Yes, you are right. You are right. It's efficiency and saving. It's a different subject.
Exactly.
You mentioned that it is yes. Therefore, it's not easy to say that just again the value, the time of the payback time is okay. And also, you have already mentioned that the design period is very important, of course, and it takes the time. And we have another question: what is the optimum timing for being a feasible project?
Okay, so I think that question is asking when should you decide that it's going to be a Passivhaus, and when should you start doing that? I think
the beginning time to audience, and of course the project and as I can see from the question, feasible project. It's not application, but only just the project time.
Okay, so I'll answer this in two parts. So in terms of when should Passivhaus start being considered in the project? It should be as early as possible, and the reason is two reasons. The first reason is Passivhaus is a different way of thinking. It's a different way of building. So the key stakeholders, the clients, the funders, they should all be on board right at the beginning, because otherwise they won't understand what's happening. So very early on at the start, get everybody on board. But the other reason to start very early is we see lots of projects which come through a little bit later. So they've perhaps already gone through the design stage, they've gone through the planning stage, and the building is already drawn. It's in a particular orientation. It's got a certain amount of glazing, and all those things have been agreed and approved. And at that point, it's very difficult to change them. And therefore, if you can get in earlier and explain just some of the basics that I've explained today, that makes that stage just that little bit different, and people make different decisions, and they come to different conclusions. So I think as early as possible. The other really interesting thing about Passivhaus is, I didn't talk about it much today, but the software that goes with Passivhaus, the Passivhaus planning package, that is used to model to see if the building meets the criteria, that is very easy to get a quick answer. So you can put in a very basic building quite quickly. You don't have to put in all the details straight away, and you can get an answer to see how close you are. So if you do that early on as well, then that will tell you, where you are. So that's sort of the three reasons really to get started really quickly. But then the other fact about time is actually the build time for a Passivhaus project it doesn't take any longer than a normal project. Once you've got the design right and you've got a good, robust design, the construction phase should be the same as for a non-passive house project.
Okay, John, we have only 6 or 7 minutes left. There's another subject. Are there any incentive in UK for building passive house?
Not yet. I wish there were, but there are some people who are beginning to think about this. There are some incentives in Vancouver, in British Columbia, in Canada, and what they've done is they've done things like saying, if you build a passive house, we will allow you to build 5% bigger. So you can build a bigger building if it's passive house, or if you build passive house, you can build a 1 story higher than otherwise you would be able to. That doesn't work particularly well in the UK because we don't zone in the same way, and we don't constrain space in the same way. So there are policies that a number of local regions are working on in the UK, which say, okay, if you build a passive house, you don't need to do all these other things. You don't need to submit an energy statement, or you don't need to pay your contribution to our carbon offset fund. And maybe the time for your application will be 7 weeks instead of 14 weeks. So things like that to encourage people to make it worthwhile for people to build a passive house are being considered. But what obviously we would like to see is that our national kind of regulations, so what our building regs say is approaches towards passive house levels, because that's the only way we'll get everyone to build to the right standard.
Of course, there is a comment, one comment, using a modular facility system would be interesting to retrofit of building in 25 seconds.
Yeah, so there are a number of modular facade, modular retrofit systems being considered. The most, I think the most famous in the UK is Energy Sprong, which is there's a trial going on at the moment, and it's a great idea. Just sort of wrapping a building in an outer shell, but there are some passive house trials going on as well to do a similar thing, because one of the things that's difficult to do in a retrofit situation is the ventilation, because MVHR, which passive house requires, has got ducts going to every room. In an existing building, that's quite difficult, but if you're wrapping the building in a shell, you can put the ductwork inside that wrapping, and you can move it around inside that insulation layer quite easily. So there are some definite advantages to that, and there are certain types of buildings where it will work. 35 seconds is probably a little bit quick, because you've got to build the panel first, and before you build the panel, you've got to measure, etc., etc., etc. So yes, it's quick, not quite that quick. But the other thing I was going to say is that there's a kind of an estimate. So the UK suffers from some of the oldest housing stock in the whole of Europe, and we're also quite attached to our houses, and we like the way they look, especially the older ones, which means that for many of our homes, people would not accept coming along and putting a new shell on the outside and changing the way it looks. So at the moment, we think it's around 40% of our homes might work with a prefabricated shell retrofit on the outside. The others, we need to perhaps work out a different system and do something different.
Yeah, we have also another last question. What do you think about the prefabricated passive house?
So prefabricated is a great way of building passive house. Mm-hmm. One of the key things about passive house is that there is much greater quality and attention to detail than you will typically get on a building site. certainly in the UK anyway. If the building sites I've visited, it can be wet, raining, cold, and there are bits of brick or timber all over the place. It's a messy place, and it's difficult to build things really, really accurately in those conditions. In a factory, you don't have that. You can build things precisely. You have computer-controlled lathes or cutting machines, which means you can build things very precisely. You have less wastage, and the crucial thing for Passivhaus is airtightness. And you can get airtightness done much more efficiently on a prefabricated panel than you can on site, because you can get machines to lay the tapes or the boards or whatever it might be. So airtightness is critical, and airtightness is probably easier to achieve in prefabricated. So you can build Passivhaus in any way you want, but I would suggest that prefabricated is a really good match for building Passivhaus buildings.
Okay, it's very nice. We have already answered all the questions, and another one is a different question. Does the trust accept members from abroad?
Yeah, I think we would. I'm not the membership expert, but we exist to promote and encourage the uptake of Passivhaus. If there are people around the world who would help do that, then yes, by all means.
It's good. Yes, therefore it's thank you, John. It's really it was a very useful session, and we have already answered all the questions. Of course, if some people wants to be in contact with you, also they can use your LinkedIn platform. That's
yep.
And I would like to express my pleasure to have conducted this session and to meet experts like you, John. Thank you very much. I'm very pleasure to meet you. Yes. Also, we would like to say thank you, Yasemin Somuncu, who took the responsibility of our session, constantly informed and managed us, and fulfilled her duty, in my opinion. Thank you very much, Yasemin. Thank you very much for your participation, reminding that you can watch the repetition of the sessions on the YouTube channel. And I would like to kindly end our session. Let me admit that we wish to come together as soon as possible in a much more enjoyable physical environment, of course, I would like. But this time, stay healthy and stay at home. Thank you. Would you like to say one word, a few words, John?
Yeah, well, I'll just say again, thank you very much for inviting me. It's great to be able to participate internationally. Thank you for everybody who's listened, and some great questions, which is really nice to see. And perhaps some of us will be able to meet in person in the future.
Thank you. Bye-bye. It's the end of this session. Okay.
Bye-bye.